anyway, and is not erasable. Okay, so at the end of the last lecture, I spoke a little bit about characteristic kernels, which are kernels for which mean embedding, so expected feature maps, are unique for every probability. And I talked about a way to measure or to determine whether a feature map was characteristic, which was basically to look at another definition, which is universality. The trouble is that universality is quite a technical definition. It's not necessarily easy to check itself. So you've sort of taken one perhaps difficult to check property and you've replaced it with another one. So that's perhaps less useful. It turns out that there's another way to check characteristic kernels, which takes a little bit more, I guess, preparation, but is actually a lot easier to use once you understand how it works. And I'm going to talk about that in the first part of today's lecture. Okay, so first of all, just a reminder, what's the mean embedding? So the mean embedding, this is like the expected feature map. And it's a function in the feature space which has the property that if you take the inner product with some other function, you get the expectation of that function. So inner product of mean embedding and f is just the expectation of f. Okay. Now you can basically use the normal trick of evaluating. So this is a function in the function space. So you can plot it, okay? You can plot it by taking its inner product with the feature map at the point where you want to plot it. So this is the usual reproducing trick. Okay. Now remember that what's the property of the feature map? The property of the feature map is it takes expectation. So it's taking the expectation of this feature map, right? And another way of writing the feature map is the kernel with one of its arguments fixed at x, like that's, as we've seen, one of the representations of the feature map. So here's the kernel with one of its arguments fixed at x. And we just take the expectation with respect to the other argument. So that function is just the expectation of the kernel, okay? So if I'm using a Gaussian kernel, and this is my distribution P, then this function looks basically like a smooth version of that distribution. Now if I used a different feature map, like a polynomial feature map, then this function would look different. It wouldn't necessarily be a smooth version, okay? But for the Gaussian kernel, this is what, this is my feature map. And then a distance between two probabilities is just the norm of the difference between the expected feature maps, okay? So this is the statistic that I'm using to compare two probabilities. Now, if my feature space is rich enough, then these expected feature maps are unique for each probability. So this means that this distance is 0 only if P and Q are the same. Okay, so this is my quick review. So now I want to determine, how do I tell whether these feature maps are rich enough that they uniquely represent my probabilities. So I'm going to use a Fourier style argument to show this. Last time I sort of began with a Fourier argument, but I perhaps leapt into it a little bit too quickly. So I'm going to start with actually the simple feature space representation that I talked about in, I think, the second lecture, which is the Fourier series representation. So let's remember, first of all, what kinds of functions we're trying to estimate. So they're functions that are on just a compact interval. In this case, these functions are just from minus pi to pi. And you can think of this interval as having a periodic boundary condition. So it just keeps repeating over and over again on each side until infinity. And because it repeats over and over again, we only need to plot it on this little interval here to get an idea of what it looks like. Okay? So for functions of that form, you can represent them as Fourier series. So you can basically expand them in terms of a sum of increasingly high frequency sinusoids. So this is what I'm doing here. So here is my function x, f of x, which is in this case just a top hat function. And I've written this as a sum of, in this case, only cosines because the sinusoids cancel out. It's a symmetric function. which are basically centered at a whole bunch of different frequencies, okay? So what I've plotted here, for each of these indices L, from -infinity to infinity, so in this case just -10 to 10, I've plotted the weights of these sinusoids. And basically, like, adding sinusoids of increasing frequency with these decaying weights is going to return me something that looks pretty close to my top hat function. So you can see it's not quite there, it's still a little bit off, particularly these borders here. But as I see more and more, like as I add more and more weights here, I'm getting something that's closer and closer to my top hat. So this is how I'm representing my function, okay? And you can do the same thing with a kernel, okay? In the case where the kernel takes as its argument the difference between the two inputs. So let's say I've got a Gaussian kernel. I'm giving as my argument just the difference x minus y here, okay? So that means that my Gaussian just takes a single argument, which is the difference between the two inputs, okay? So because it takes just a single argument, I can write this Fourier series expansion, and it turns out that the weights have a Gaussian decay as well. So here are my Fourier series coefficients, which are going to return me, in this case very accurately, this Gaussian shape here. And these are decaying exactly as a Gaussian as well. Okay? So this is my kernel Fourier series, and I've shown Fourier series of the functions. So how is this going to help me when I'm trying to compute the distance between two expected feature maps? What I'm going to do is actually represent my distribution, which I'm getting expected feature map of, in terms of its Fourier transform. Okay, so if you have a probability distribution, you can take its Fourier transform. So you can express it as this Fourier series representation. Okay, as a sum of sinusoids. Like a Gaussian, we've already seen. You can represent it as a sum of sinusoids. Okay, now the trick is, remember the mean embedding is the expected kernel. We can also do this in this Fourier space. So we can do the same operation, this expected kernel, in the space of Fourier coefficients. Okay, so in the space of the scalings of these sinusoids. And it turns out that this is an easier operation in the Fourier series space than it is in the initial space. And specifically, all that you need to do is to multiply together the Fourier series coefficients of the kernel with the Fourier series coefficients of the probability. This will give you the Fourier series coefficients of the mean embedding. So you can look this up in textbooks. It's called the convolution theorem. But basically, all that you need to remember from it is that this operation here, which is the convolution of the kernel of the probability, so the expected kernel, can be done in the Fourier series space just as a product of the Fourier series coefficients of the kernel and the Fourier series coefficients of the probability. Okay? So now we have a way to take this operation in the space of Fourier series coefficients. We can use this to compute the maximum mean discrepancy with this Fourier series representation. Okay? So remember that the mean embedding can be written as a product of the Fourier series coefficients for the probability with the Fourier series coefficients of the kernel. Okay? And then we multiply this by this sinusoids of increasing frequency, and we get back exactly the mean embedding, okay? Because we've just taken out Fourier series coefficients, we multiplied it by the sinusoid, and we get back the mean embedding, okay? And we do this with Q as well, our second probability. So what we've shown is that the mean embedding between P and Q can be written as the difference of Fourier series coefficients of P and Q multiplied by the Fourier series coefficients of the kernel. Okay, then you multiply these by their respective sinusoids, and then you take the RKHS norm. So remember, this is a penalized norm, which is penalizing high frequency coefficients of this. Okay, so you can look that for the later. And so a characteristic kernel on this domain is a kernel for which this object here, which is the distance between P and Q, is 0 if and only if P and Q are the same. Okay? So from this representation, I think it will start, you should start to get an idea of how this is going to work. But are there questions up to this point, or is that good? Okay. So now let's look at an example. So remember, I'm on this this minus pi periodic domain, and this is sort of rotating on and on and on. And I've written here, this is the probability of x. You'll notice that the probability of x is just flat. So what I'm saying is that the probability of observing a point x is uniform over this entire minus pi range. Okay? And now my q is pretty close to this, but what I've done is I've added to it a sinusoidal perturbation. Okay? So I'm slightly more likely to see points here, slightly less likely to see points here. Okay? Now I want to tell these two things apart using maximum mean discrepancy. Okay? So what does the Fourier transform of this look like? Well, all that is actually a single coefficient, which is the coefficient at the frequency 0, because this has no sinusoidal components at all. All it is just a flat line. Okay? So that corresponds to 0 frequency feature. This one has the flat line, which is basically this offset here, but then it has these two bumps here. Okay? These are the features that give us a cosine at that frequency. Okay? So from this I get here, from this I get here. And this is my Fourier series operation. Okay? So I've got a Fourier series representation of the flat one, I've got a Fourier series representation of this one. Remember the maximum mean discrepancy, I needed to take the difference between the Fourier series coefficients. So what do I get when I take the difference? I get pretty much just these two things here. Okay? Because this flat thing is just the same, it's just flat, and then all that's left is, I mean, the flat thing is equal for both of them, so all that's left are these side lobes here. Okay? So what I get from my difference in characteristic functions of the probability is just two bumps here. Okay? So now I need to multiply the difference in the Fourier series of my probabilities with the Fourier series of my kernel. Okay? And that gives me the Fourier series of the product. So what if my kernel was Gaussian? Okay, so here's my maximum mean discrepancy, difference in Fourier series coefficients multiplied by Fourier series of the kernel, and then I use those to expand out my nonlinear functions. So in this case, who thinks that the Gaussian is characteristic? Most people should think it is. The reason is because this is never 0. Okay, so this product here is never going to be 0. Okay, so basically this function will never be the 0 function. So what would the problem would be if this was 0 anywhere, then this product could be 0, and so even though p and q were different, the product would still be 0, and this entire expression could be just a 0 function, and the norm of the 0 function is 0. So this is a characteristic kernel for this domain. So having given you a clue, is this kernel characteristic?
No.
Yay. So I've set this up to be 0 in exactly the point that it needs to be, which is zeros at these points like 4, 8, and so on, which is exactly the points where this thing is non-zero. This is non-zero at the coefficient 4. So if I multiply this by this, I'm going to get 0. Okay, so then this whole thing is just going to be a big 0. The norm of the 0 is 0. And so even though p and q are different, nonetheless, I found a kernel for which the distance between these p and q is 0. Okay, so that's not characteristic kernel. Okay, so characteristic kernels on these periodic domains are actually really, really easy to tell. You just get the Fourier series of the kernel. Is it 0 anywhere? Yes, it's not characteristic. If it's not 0 anywhere, it's characteristic. So the moment you can get a Fourier series representation of your kernel, you're done. And you can look up Fourier series of most functions just in textbooks. So it's a very quick and easy way to check whether a kernel is characteristic or not. Okay. So that's fine for functions on this periodic compact domain. A lot of the time, though, we care about kernels on RD. Okay, so just like a Gaussian kernel on the real line, or a Gaussian kernel on the two-dimensional real plane, and so on. So knowing how to do or how to test for characteristicity on a compact domain with periodic boundary doesn't actually tell us, you know, a lot of the answers that we care about in a lot of the problems that we're looking at. But it turns out that the trick that we use to show characteristic is actually very, very similar, even on RD, to this Fourier series way. Okay? So again, we have the characteristic function of a probability. But before, we had this as a sum over nonlinear features. Now, because we're on RD, we actually have an integral over you know, the entire RD space. And now we get a continuous function of a d-dimensional variable rather than just a set of coefficients. So I've replaced my sum by an integral, but the idea that you should have in your head is the same one, that this is a way of building up a probability using a whole bunch of sinusoids. But now, rather than, you know, countably infinitely many of them, there's uncountably infinitely many. So you've got like a whole continuum of sinusoids you're using to build up the P. Okay? So this is the Fourier transform of P rather than the Fourier series representation of P. Now, if your kernel is translation invariant, there's a theorem which is quite interesting called Bochner's theorem, which tells you that any positive definite function, which is a function only of the difference in its argument, can be written as the Fourier transform of a finite and non-negative measure. Okay? So what's the example of a finite non-negative measure? Well, the Gaussian is an example. So if my kernel, can everyone read that? This is yeah. So let's say I've got this function here. So this is a function of omega, and it's integral, so it's finite, and it never goes negative. Okay. So let's look at a different example. So if I gave you a kernel, which is k of, you know, x minus y, and this kernel looked like this. So this is x minus y, and this is the kernel function. It's just the top hat function. Okay? So does anyone think that this is a kernel? Does anyone think it's not a kernel? So let's look at its Fourier transform. The Fourier transform, now I've got the frequency here, and now I've got the Fourier transform. That looks like this. It's the sinc function. Sine omega, omega. So from this, can you tell whether this is a kernel or not? So remember this point. So this thing here goes negative. So it's not a kernel.
It's not a characteristic kernel.
No, it's not a kernel at all because it goes negative. So the characteristic kernel, a kernel which isn't characteristic is 0. But as soon as you've got something whose Fourier transform is negative, it's not even a kernel anymore.
Right.
Yeah. So yeah. Now, what if I replace my top hat function with a triangle function? Okay. Now the triangle function is the convolution of the top hat itself, which means the Fourier transform is just the square of this function. So the square of this function now looks like this, more or less. And so now it's non-negative. So this is a legitimate kernel. It goes to 0 at some points, but it never goes negative. Okay? Now here's a interesting one as well. Imagine in my Fourier domain, I have a function that's just flat everywhere. Is this going to be a kernel? It's not negative. It's not finite. Exactly. That is actually the Fourier transform of something which is a spike which goes to infinity at 0. Okay? And this spike going to infinity when x minus y is equal to 0 is not a valid kernel because it's the Fourier transform of something that isn't finite. So these are like some examples. Okay. So just as I did with the Fourier series, I can write the maximum mean discrepancy using this Fourier representation, okay? So, here I've got the difference in the characteristic functions, which are the Fourier transforms of my probabilities P and Q. I've taken the conjugate here, that's a bookkeeping thing. Then I multiply that with the Fourier transform of my kernel. I take the inverse Fourier transform, which is the same as sort of the operation of summing over the sinusoids for the Fourier series case. I take the RKHS norm of this, okay? And what I want to determine is whether this quantity here is 0 if and only if P and Q are the same, okay? So just as in the Fourier series case, let's say now I have a Gaussian, and I have a Gaussian which is perturbed by a sinusoid. Now these Gaussians are on RD, like these go on until infinity. I've just plotted it until a finite number of points. What you'll notice here is that the sinusoidal perturbation here does not have constant amplitude. It decays to 0. So the reason for this is that this Q is a probability. If my sinusoid had constant amplitude, at some point when I added that to a Gaussian, it would go negative. And you can't have negative probability densities. So, you can't just add a sinusoid as I did on the periodic domain, because, here I have to have a density that has to integrate to 1, so it has to decay somewhere. And, if I add a sinusoid with constant amplitude to it, at some point it's going to go negative. So is that clear for everyone? Yeah?
The irregularity in it, is that just because the way you plotted it?
Yeah, I mean, this is just it's a sinusoid, but it is literally just a sinusoid with a decaying envelope. Yeah, so if that looks a bit peculiar, it's plotting out of that. Yeah. Okay, so what does this look like when I take the Fourier transform? So remember now, this is like analogous to the Fourier series, but here my set of sinusoidal features is infinitely, well, uncountably infinitely large. So you've got sort of a continuum of frequencies that you're integrating over, rather than a discrete set of frequencies you're summing over. Okay? So Fourier transform of a Gaussian is a Gaussian. The Fourier transform of a Gaussian with the sinusoidal wiggle on it, it's a Gaussian, but then on each side of it, it's got a spike. So remember when I had my flat function and I added a sinusoidal perturbation, there I got just a single coefficient here. Now here, rather than getting something that's infinitely thin, I get something a little bit wider. And that's because I've required my sinusoid to decay, and so that has the effect in the frequency domain of sort of adding some frequencies to each side of the sinusoid, which sort of force it to decay away as you get away from that central point. Okay? But the main point is that you've got a Gaussian and you've got on each side of it these things that are roughly sinusoidal, but a little bit more spread out. Okay. So let's take the difference in these characteristic functions, and we get this. So all that we've got left are these two spikes on each side. Okay. And then we're going to multiply this with the Fourier transform of the kernel, which we've said is a non-negative finite measure. Okay. So here's the Gaussian kernel. Here is the difference in the characteristic functions. So in this case, do we agree that the kernel is characteristic? Yeah. So here is a function, this top hat function. Now this is a legitimate kernel, okay, because now I'm in the Fourier domain. So this is something that's finite. It's something that's non-negative, okay. So if I do the inverse Fourier transform, I get the sinc function, but in my original domain rather than in the Fourier domain. And so the sinc function is a valid kernel, okay, because its Fourier transform is a top hat. But the top hat is not a valid kernel because its Fourier transform is the sinc, and the sinc is negative. So is that distinction clear? Yeah. Okay, so this is a valid kernel, but evidently it's not a characteristic kernel. The reason it's not a characteristic kernel is because when you take the product, in this case you can see it's 0, so we found a good counterexample. Yeah.
Sorry, can I just go back and ask what you mean by the condition of being finite? Does that mean it? Because you talked about it in the original domain, saying it was a spike, an infinitely high spike.
Right, right.
Does this also mean that it integrates to a finite quantity in,
yes,
in the
Fourier
frequency Fourier domain?
Exactly, that's right. Yep. Okay. This one is tricky. So remember the triangle kernel. So I will take a poll. So who thinks it is characteristic? Who thinks it is not? That is the right answer. Oh wait, no. I lied. Okay. In this case, it's going to work, right? You take the product of these two things, and it's going to be non-zero. But can it be that P and Q differ such that they're? I mean, can you basically find a P and Q which differ only on these points here? Okay, like on some countable set of points in the Fourier domain. And it turns out that you can't, because like if you remember like the Fourier series, this is something that sort of has this periodicity about it, so it sort of goes on and on forever. If you represent the difference in P and Q just at this countable set of points, it's the difference in P and Q will never decay, and this is a problem because that's sort of saying that at some point the density is going to go negative. So like imagine you have so just for that simple case we talked about, you've got a Gaussian, you've added to it a sinusoid of constant amplitude. What you're going to get is something that's like, this is the center, it's going to go like this, right? And at some point, the density is going to go negative, okay? So basically, you need this perturbation to decay and not to be periodic. And the moment this perturbation decays and isn't periodic, you can't represent it like as this sort of countable set of points. So there's basically no way that you can find two probability distributions that differ on these sets, which are sets of measure zero. They're just at individual points. You can find P and Q that differ on a continuous interval, but you can't get them to differ only on these sets of points. So, like, surprisingly, this triangle kernel is a characteristic kernel. Okay? So the general rule for, say the general rule first. The general rule for characteristic kernels is that basically, like, there cannot be zero on an interval in the Fourier domain. There can be zero at individual points. There can be zero at infinitely many, countably infinitely many points, as the sync kernel is. But they're not allowed to be zero on an interval, because the moment they're zero on an interval, you'll just find a difference. You'll find a P and Q, which are different only on that interval, which I can always do. Like here is exactly how I would make such a case. And then it's not characteristic anymore. So is this example clear for everyone? Yeah? Okay. Yeah?
Did you prove before why the Kernel has to have a positive Fourier?
No, I just stated the theorem. I did not prove it. Yeah. So the proof is, in Bedland's book. There's a couple of books where you can see it proved. Yeah. So just because a kernel is characteristic doesn't mean it's any good. This is important. So here are a bunch of different Qs where I've perturbed my Gaussian with sinusoids of increasing frequency. So what does this look like in the Fourier domain? Well, in the Fourier domain, these spikes here are getting further and further up into the high omegas, okay? Because basically, like, this is increasing frequency of the feature that you're adding, okay? So as the sinusoid gets, like, rougher and rougher, the frequency here gets larger and larger, okay? Now, what I've plotted here is the distance between P and Q, so the distance between a Gaussian and the Gaussian perturbed with the sinusoid, as the perturbing frequency increases, so as I go from here to here to here, okay? And what you'll notice is that the maximum mean discrepancy is dropping off, okay? Now you should at least have a good intuition for why it is that the distance between P and Q is getting smaller as the difference in the characteristic functions occurs at higher and higher frequencies. This is because, remember that the norm in the RKHS penalizes high frequencies, okay? So if the difference between P and Q is a high frequency function, now remember when I wrote the Fourier series norm of an RKHS function, this is equal to the sum over L, FL, FL, conjugate divided by KL, right? This is the norm in the Fourier series case. So because the Fourier series of the kernel are decaying, that means that, you know, for this norm to be finite, these have to decay even faster, okay? And so basically, you know, this implies that the norm of a non-smooth function, yeah, wait a second, I'm confusing myself. I need to think about that a bit. Oh yeah, no, I know why. Because the MMD, you're forcing a smoothness constraint on the function that you're using, which is that the MMD, if you write it in the function representation, is sup of the norm of f less than or equal to 1 of the inner product of f and up minus q. So I think probably the quickest way to see it is actually to go back. Yeah, let's see. So I'm not sure if that intuition is a good one. I think the best intuition is, okay, first of all, to notice that the function here, if this differs at high frequencies, then this is going to penalize it. Yep, this is going to work. Okay, now I know how to show it. Let me, and permanent. I will not use that. It's not too permanent. I think it's pretty permanent. Okay. I have enough space to write what I need to write. Okay. This is actually still true, so I'm going to keep that up there. Now, my FL is going to be basically this difference, phi p minus phi q, multiplied by, and there's an L here, multiplied by the Fourier transform of my kernel KL. Okay? So, if I then take the norm of this function here, what I'm getting in the numerator is the kernel squared, KL squared, times PL minus QL squared, divided by KL, right? So that means that as the difference in the characteristic functions increases in frequency, because the KL is Gaussian and this is decaying, this whole norm is going to decay. Now it works. Okay, is that clear to everybody? Yeah? So this is why when P and Q differ at high frequency, the maximum mean discrepancy between them is going to decay. Okay? Because if these differ at only high frequencies, like the higher the frequency at which this difference is non-zero, because the kernel has a decaying Fourier series, this whole thing is going to decay. Yeah?
Can you get the same thing from the fact it's finite, in the sense its mass will have to be restricted to some area, some frequency range, and have to decay outside that area to keep the whole mass finite, and therefore it can only pick up, it can only accentuate differences at some restricted range of frequencies.
I think the size of the perturbation, at least in amplitude, is constant. So if you sort of think about, like, say this sinusoid here versus one that does sort of two wiggles, like I'm not sure if, like, thinking of the total area of the perturbation is...
I was thinking of the area of the Fourier transform. The Fourier transform of your kernel has got to be finite.
Yep.
Therefore, since you're multiplying by that,
that
can only pick out some area.
Sure. Yeah, no, that is exactly right. Yeah, exactly. Like the kernel has to be finite. That means it has to decay at some point. I mean, it can't just keep going up.
But it could be zero in the middle and have some mass further apart.
Yeah. No, it just has to be
space.
exactly like the Fourier transform of that finite non-negative measure. And so, yeah, but exactly as you say, because it's finite, that means that somewhere out here it's going to have to decay. Like, we don't know how far out, but somewhere out here it will need to decay. So at some point this thing is going to have to drop. And so the Fourier series. And so yeah, that means that as we get higher and higher frequency, at some point the norm is going to decay. Because the Gaussian has this very simple decay pattern, in that case you get a very simple decay pattern for your kernel. Okay? Now, what happens if I use the triangle kernel? This is my decay pattern, and that looks appalling, okay? Because there are some frequencies at which I'm getting an extremely small, non-zero, but extremely small distance, okay? So why is that? So let's go back to the triangle kernel. Basically, the moment that my difference in distributions occurs near this frequency, even though this product is not zero, it's very close to zero, okay? So this kernel is a terrible kernel if my P and Q happen to differ near this frequency. So even though I can distinguish any P and Q, there are some P's and Q's which are different in such a way that they become very hard to distinguish with this kernel. So it is kind of like a slightly pathological case, like you have to sort of construct this example in a reasonably artificial way, but it's still something to bear in mind, that just because you can guarantee that this is a characteristic kernel and that this distance is zero only when P and Q are the same, doesn't mean that every kernel is equally good. And some kernels actually might have some quite tricky and perhaps unexpected flaws about them, which, this is an example of a kernel which has such a flaw. Okay, so is that example clear? Yeah? Okay. So the characteristic kernel, like this is the main theorem. The property is that if the support of the Fourier transform of the kernel is the entire domain, so if it's zero only on like these, countably many points rather than on intervals, then the kernel is characteristic. Okay. So what's interesting is that if any kernel is continuous and has compact support, then it's characteristic. Okay. So as long as, like, a nice example of this property, is this kernel here, this triangle kernel. So it's continuous, and the support is compact. So the Fourier transform of this triangle looks like a sinc function. The Fourier transform of any continuous compactly supported kernel is going to have this sort of property of only being zero at single points, not ever zero on an interval. Okay? And so these kernels are always going to be characteristic. And for the proof, you can see the paper, but the property, at least intuitively, I think is clear. So this is just a sort of pointer to the further literature. There are a lot of domains in machine learning where you might want to have a characteristic kernel. So for instance, in robotics, you have orthogonal matrices. If you're doing a kernel on orthogonal matrices to perhaps represent joint angles, you might care that your kernel is characteristic. You can prove an analogous property for this case. We've seen periodic domains already, because there you've got a sort of Fourier series representation. Also in computer vision, people often deal with histograms, like color histograms or so on. And you might actually want to put a kernel on those histograms. And it turns out that you can also prove that if you've got a distribution over histograms, so like a distribution over distributions, you can get a characteristic kernel for this case. So all of these cases follow from pretty much the same kind of Fourier argument as I've shown here, just for RD and for the periodic domains. But the, I guess, upshot is, like, if you have a domain in robotics or vision where you want to make sure your kernel is characteristic, you can sort of make an appeal to the literature and use a kernel which has that property. Okay. So I think that's, everything for characteristic kernels. Other questions up to this point about characteristic kernels? No. Okay. So the next I guess, section of the lectures is going to be on hypothesis testing. So I want to just start with motivating problem. So since I'm in a neuroscience lab, I need to sometimes work on neuroscience problems. So what I have plotted here, time series recorded in the brain of a signal called local field potential. Okay, so what I've got here are 50 time series of this signal in the presence of a large neuron spiking. So somewhere in the middle of this, a large neuron starts spiking. And this local field potential is sort of the aggregate electrical activity of all of the neurons nearby. And the sort of conjecture is that these neurons might be sort of providing feedback or providing input or whatever, and so they should be doing something different if one of these large neurons spikes. Here is the local field potential in the absence of a spike burst. So from these two time series, I can't see any important difference. So let's now look at an average over 50. So I've got like the mean in bold here, and then the standard deviation is a sort of like error bar type thing around it. And again, just looking at this plot, you know, the red curve is where a spike burst happened, the blue curve is where one didn't, and I can't, again, see a difference between them. If I go to 500 data points, now I'm starting to see a difference in the averages, okay? So, you know, here I can sort of see like a spike burst happens as in, you know, it's in a sort of centered point here. You can see there's somehow a suppression of activity, and then like the activity goes up, like maybe it's sort of feeding back to the neuron to sort of prevent it from spiking too much, okay? So what I want to do is basically, like, if I get these, like a data set like this, I want to basically tell, like, is there any significant difference, like meaningful difference between these two, or is any difference between them small enough that it's only due to chance, okay? So this is what I'm trying to get at in the next slides. I'm going to sort of talk about what it means to be like a chance level versus at, you know, significant level, okay? So for this, I'm going to introduce some terminology from hypothesis testing. So I have here basically two hypotheses, which is the null hypothesis, which is that there's no difference between my, you know, brain signals when there's a spike burst and when there's not, and the alternative hypothesis, which is there is a difference, okay? So I get samples from P. You know, these are my waveforms from the spike burst case. These are my waveforms from the non-spike burst case. And I use the empirical maximum mean discrepancy between these, okay? So now what I want to do is say, well, is this distance far from 0 or is it close to 0? If it's far from 0, I think it's unlikely that P and Q are the same. So it's very unlikely that this big distance just came about by chance. If it's close to 0, I'm going to accept the null hypothesis. I'm going to say it is quite likely that this came about by, you know, this is sort of in keeping with the kinds of differences one might expect when P and Q are the same. So this is fine, but it kind of leaves open, like, far from 0, close to 0. Like, how do I determine, like, how far is far enough before I say it's unlikely? Okay. So one way to do this is basically to look at something which is the asymptotic distribution of the statistic. So that what it means is that my distance between probabilities itself has some kind of distribution when I compute it in my sample. Okay, so here is my distance computed on the sample. So remember, I mentioned earlier how to compute this, but what it amounts to is the average kernel between points within P, average kernel for points within Q, minus the average cross kernel between P and Q. So P and itself are on average as similar as P is similar to Q. Then these average sort of similarity levels all cancel out. This whole thing goes close to 0, and then this distance is close to 0. Okay, now I'm going to show on the next slide what I mean by this, but like if P and Q are different, if I sample a lot of examples of P and Q, and I compute a lot of distances between them, then this is going to have a Gaussian distribution with this variance. I hope I've plotted it. Yes, I have. Okay. So here is P and Q. So P and Q are both Laplace distributions, but they're different. So basically, one has a higher variance than the other. Okay. Now what I've done in this plot is I've drawn a whole bunch of P's and Q's, like a whole bunch of samples from P and Q, and I've computed for each of those samples the distance between them. Okay. And then I've done a histogram of all of these distances. So I've basically repeated this experiment many, many times. I've drawn a sample from P, drawn a sample from Q, computed the distance, put it on the histogram. And you can see that this histogram has a Gaussian shape. Okay? So this is what I mean when I say it has an asymptotically normal distribution. Like, assuming that you've seen enough samples of P and Q and you've used that to compute the distance, if you compute a whole bunch of these distances, this is going to look like a Gaussian. Okay? So asymptotically normal. So this is the case when P and Q are different. So is that example clear? Yeah. And the cool thing is that I can compute its variance in closed form. So this expression here, I can replace these expectations. So like I'm using Z as a shortcut to say X and Y together. Okay, I can compute these expectations just on the basis of samples. This means like Z and its independent copy. Yeah. And you have a closed form expression for this variance. So you can actually predict what this Gaussian is going to look like. Okay. Now, what happens when P and Q are not different? Well, then things get quite unpleasant. So here is the asymptotic distribution of the distance between P and itself. And this, you'll notice that it's not a Gaussian or anything nice. It's an infinite sum. And the weights of this infinite sum are given by the solutions to this eigenvalue problem, a functional eigenvalue problem, where here is my kernel, and here is the probability that I don't know. So this is not very nice. So this is actually like an infinite weighted sum of chi-squareds. I can plot it. It doesn't look anything like a Gaussian. It's very skewed. But in this example, what I've done is I've just said P and Q are both Gaussian. They're the same Gaussian. Compute the distance between them, put it on a histogram, and then do it over and over again. Like, draw samples from the Gaussian, draw samples from the same Gaussian, compute the distance between those samples, plot those distances in the histogram. So you can see that the distances are not zero, okay? And you'll see even that some of the distances are negative, which is odd. The reason why the distances are negative is because I'm making an unbiased estimate of a distance whose mean is 0, okay? So on average, my distance is going to be 0 between P and Q, but because I'm drawing samples of a distribution whose mean is 0, some of these samples are going to be below 0, some of them are going to be above 0. So, I'm computing just an estimate of my distance. And this estimate has the mean, which is 0, because the mean distance is 0. But the estimate has some noise. And the noise can either be positive or negative. So that's why I've got these negative distances. So I could add like a bias term to my distance to push it up above 0. But then I would no longer have the right expectation. So if I added like some extra terms to make sure I only get positive empirical distances, then the more the expectation of that expression would no longer be correct, because its expectation would no longer be 0 as it should be when P and Q are the same. So this is, even though it's a little bit unintuitive to get negative distances, this is actually the correct way to do it when you've got finite samples. Now obviously, as you see more and more samples, this is going to squeeze down to something which is concentrated around 0. So in the end, it doesn't matter if some of them are a bit negative and some are a bit positive. Like, you're going to get the right answer as you see enough points. Okay. So let's return to the question that we're trying to answer. The question is when is it unlikely that my distance, my true distance, is 0? Okay. So if I observe a distance out here, then it's pretty unlikely that my true distance is 0. But if I observe a distance here, then it's pretty likely that my true distance is 0, because on this histogram of 0 distances, this is pretty likely, this is not very likely. So what I want to do is I want to find, say, like the 95th quantile of this distribution here, so that like 95% of points are going to fall below some threshold. So that's a pretty smart threshold for determining whether, you know, and then this distance is large, okay? So that's a reasonable threshold. The trouble is, this thing is not very pleasant, so how do I compute it? So there are a few tricks. So this is our goal. We want this threshold such that the probability of exceeding this threshold when P and Q are the same is less than like some very small number. So then it's very unlikely that such a big distance was seen by chance, okay? So I think the quickest and easiest way to get this threshold, and the one that I would certainly recommend, it's the one that on the software package on my page it defaults to because it always works, is this one here, the permutation test. So what do you do? What you're trying to do is basically like to fake this histogram, okay? So what you get, you have your samples from P and Q, you merge them all together into a single bag of samples, then you randomly assign 50% of them to P and 50% of them to Q. Okay, so it's like you're scrambling your P and Q together, and then you compute the distance between that scrambled sample. And then you scramble them again and you compute the distance. You repeat that, and then you get a histogram like this. So if P and Q are different, you would get the distance between a sort of equal mixture of P and Q and itself, okay? Because you've sort of like completely randomly permuted the identity of P and Q. If P and P are the same, you're just going to get this histogram because you're just basically saying like draw two samples from P, compute the distance, okay? So either way, this permutation approach is a reasonable one. It's going to give you, like I said, like a histogram, which is going to look, you know, as long as the number of samples from P and Q is large enough, the histogram is going to look pretty much like that. So is this idea clear to everybody, how to do this permutation test? Yeah. So if you've got some number and you want to tell whether it's significantly different to 0, and you're computing it on the basis of samples, then this kind of permutation style argument is always like a good one to use because you don't need to sort of think very hard about it, you just like run the code. Where it's, I guess, a little weak is that it takes, or it can take an awfully long time to sort of, you know, you have to recompute your statistic 500 times. And if you are in a hurry, then that can be painful, okay? Another neat trick, which is true for the maximum mean discrepancy, is that you can compute the moments of this distribution in closed form. So even though this thing looks horrible, you can compute its variance, and the variance doesn't look much worse than this kind of expression here. It's something that looks a little bit like that. And not only that, but you can also compute, like, you know, the third and fourth moments of this thing in closed form. Like, there's a lot of bookkeeping to be done, but you can still compute them. And then you can say, well, if I've got the first 4 moments, I'll just fit some family of distributions which have 4 moments, and it's probably pretty close. And a lot of the time, probably pretty close is right. So here is this exactly the same example from this slide here. I've got the 2 Gaussians. You know, the distance between them is 0 because they're the same Gaussian. Here I've plotted in blue the cumulative distribution function, so you know, the probability of being lower than this number here. Okay. And next to it I've plotted the fit that I get from just computing the first 4 moments and fitting some parametric one. So even though I'm fitting infinite weighted sum by a simple parametric distribution, nonetheless the fit is pretty good for this example. And it's actually really hard to find a case where it doesn't work, because we were trying for the purpose of this final paper, which I'll talk about. You can also compute finite sample bounds if you know about these from other courses, but these basically are very conservative estimates of the probability of something being large, and they're not very useful. This final approach is a neat one, which I'll just mention, I guess, for its elegance, but this won't be on the exam. So what you can actually do is you've got this infinite weighted sum here. So this is the null distribution. So the distribution of these distances in the case when P and Q are the same. You can approximate these eigenvalues here, okay, which are the eigenvalues of this sort of kernel eigenvalue problem, with the eigenvalues of the kernel matrix across the samples of P and Q. So you compute a kernel matrix across all of the samples from P and Q. You get its eigenvalues, and there's only 2 times m, where m is the number of samples of these things. So it's not an infinite sum; it's a sum that only goes up to 2 times m. But these things are decaying very fast, and then you use these empirical eigenvalues in this sum. So this is actually quite a bit faster than computing the statistic, 500 or 1,000 times, particularly since generally these eigenvalues of the kernel matrix decay so fast that you only need to keep 10 of them or something, and then you don't have to compute any more. Now the good thing about this is that unlike the method of moments, this thing here, as you see more and more samples from P and Q, is going to give you the correct threshold. So this is going to converge to the right test threshold always. But it can be a lot cheaper than the other method that always converges to the correct threshold, which is this Pearson one. Which is the permutation one, where you scramble the samples up. Okay. So yeah, I mean both of these you can download software for. But yeah, this one is quite neat. But yeah, the sort of reason I brought this up is because I wanted to try and find a case where this would work and this didn't. And in the paper, we have such a case, but it took us like a month of looking for it. So a lot of the time, this thing works really, really well. And, it gives you an answer. The answer is pretty quick. So yeah, if you want like a quick idea of whether there's a difference or not, you could just start with that. If it tells you that there isn't a difference, but you're pretty sure there might be, then you could use something fancier to check your answer. But a lot of the time you're going to get the same answer from both. Okay. Okay, so that's all the stuff for testing. So are there questions about this part? So the next point that I'm going to talk about are kernel dependence measures. So just as a reminder, I guess a couple of lectures ago we talked about using the maximum mean discrepancy to tell whether x and y are dependent. So x and y are dependent when the joint distribution, pxy, is different to the product of the marginals. Okay? So how we propose to determine whether the joint distribution is different to the product of the marginals is to look for a smooth function which had a different expectation under the joint distribution and under the product of the marginals. And what we saw is that this amounts to finding the distance in a reproducing kernel Hilbert space of the embedding of the joint distribution and the embedding of the product of the marginals. Okay? So what I've shown here is a smooth function which has large amplitude where the joint distribution is most different to the product of the marginals. So here, x and y are drawn according to some distribution where they're dependent, because knowing x tells you something about where y is. Here I've drawn a function which is a smooth function, and its amplitude is largest where pxy is most different to the product px2y. Okay. And so this function maximizes the difference in expectations, maximizes the mean discrepancy. One could equally write it as the difference in feature expectations under the joint and product of the marginals. You'll remember I had a quick discussion about what kernel to use to get a feature mapping for a joint probability, and we concluded that one reasonable kernel to use was the product of the kernels on each domain. So if one of your domains is images, one of your domain is captions for images, you've got a kernel on a pair of images, you've got a kernel on a pair of captions, so these are large when the images are similar and small when the images are different. Then a kernel on image caption pairs is, one good kernel is a product of the kernel on image pairs and the kernel on caption pairs, because if the images are similar, the captions are similar, then the product is large. If either of them is small, the product is small. So the similarity of this pair to this pair is small, And if both of them are small, then the similarity of this pair to this pair is very small. This product is very small. So this is like an intuition. So this is one way in which one can determine, I guess, similarity. But it's also not necessarily a very intuitive one. Because like if I give you a contour plot like this, it's kind of hard to see why x and y have any sort of dependence for a plot like that. It's not very informative. So I'm going to talk about a more informative way of using kernels to think about dependence. It turns out that it is related to this approach, but it will take quite a bit of sort of math to get there. But I think it will be a better sort of intuition. Okay, so let's say that x and y are dependent. So here, of course, x and y are dependent, like x0, y is here, and x minus 1, y is here, so we know something about y and x. But if you compute the Pearson correlation between x and y, it's exactly 0. So if you fire up MATLAB, plot core of x and y, you're going to get 0. If you run a test, it's going to show you that there's no dependence. But clearly there is dependence. So what's a nice way to determine whether x and y are dependent from a plot like this? Okay. So one way to think about how to get dependence is to find, like, imagine you could find a smooth function that maps x to some function of x, and a smooth function that maps y to some function of y, which creates a high linear dependence. And then I can use just my standard linear dependence test for it, okay? So if I can find some mapping of x and y that allows me to see a very simple linear dependence between them, then it's very likely that x and y are dependent. Okay. So here is a smooth mapping of x and y that has that property. So here is x and here is f of x, and here is y and here is g as y. So I'm mapping x through this function, and I'm mapping y through this function. And what I'm getting out is something that looks like this. So like these functions, you can even sort of visualize it. So imagine you take this on a piece of paper and then you fold it twice. You're going to get something like this. And this is sort of the first fold, and this is the second fold. So that's how to sort of think about why these are sensible functions. And having made this mapping, you can see now the linear correlation is really high. So a way to think about dependence is, if I can find a simple mapping of my variables which has really high linear correlation, then it's very likely that they're dependent. If these mappings were like really, really complicated functions, I mean, you could imagine I give you a completely random scattering of points with absolutely no dependence. And then I have a function that just like takes them all and arranges them on a straight line. I mean, that's possible, but it's also pretty boring. So this smoothness, like as in maximum mean discrepancy, smoothness matters. If you can find a simple function to make this dependence, then it's likely that x and y are strongly coupled. If you can't find a simple function, then you can find a complicated function, but it doesn't really mean anything. Okay. So this is like the intuition that I'm going to now try and sort of set up some math for. So what I've plotted on the previous slide is something called the constraint covariance. Okay. What I've done is to look for functions with RKHS norm, in fact, well, less than or equal to 1, but these solutions when it's exactly equal to 1, of the covariance between f of x and g and y. So basically, like, I'm looking for a smooth function, so this is this norm constraint here, of x, and a smooth function of y that maximizes the linear covariance between f of x and g of y. And in the case where I can use a Gaussian, kind of what I showed on the previous slide is exactly the functions that maximize this covariance. Okay. Now, again, characteristic kernels are very powerful in this case because you can prove that if you use characteristic kernels for this mapping and for this mapping, then this will be 0 if and only if x and y are independent. So again, like if you have this characteristic property, then you've got something which will find every possible dependence between x and y. So, again, as I've mentioned, like some kernels are better than others, but with enough examples, you're eventually going to find this. Okay. But to actually sort of, well, compute this and understand what it means, I need to introduce a notion of covariance in feature spaces. So like I've already talked about a mean function and talked about how you can take expectations as inner product with the mean of the feature map. So now what I'm going to do is introduce the notion of a covariance between feature maps. Okay, so you've got these two infinite dimensional feature maps. I want to get the covariance between them. And I'm going to show that, you know, looking for a function like this amounts to performing an operation on this infinitely large covariance object. Okay. Now, if I can do that, then it also shows me how to find better dependence measures than this one. Okay. So, what does it mean to think about covariance? Okay. So, if I was doing linear algebra and all my variables had zero mean, then the covariance between x and y would just be the expectation of x and y transpose. Okay, so you've got your x, which is a column, you've got your y transpose, which is a row. You take this expectation. This is the covariance matrix between the random vectors x and y. Okay. And this covariance matrix has the property, which you can verify pretty easily, that if you take a function f and you take the f transpose cxyg, this amounts to taking the expectation of f transpose x and g transpose y. So if you think of f transpose x as being like a linear function of x, which it is, and g transpose y as being a linear function of y, then you've got this operation that, you know, f transpose cxyg is exactly the covariance between this function of f and this function of g. Now, in the previous slide, we had the expectation of the covariance of an RKHS function of f and an RKHS function of g. Okay, and what we want to do is to find like some covariance object in the infinite dimensional feature spaces that has exactly this property here: the inner product of f and the action of this operator c on g is equal to the covariance of this function f of x and this function g of y. Okay? So basically we want to make these dot products in feature space. So everything is now going to become infinite, and you get like all of those sort of usual problems that you run into when infinities arise. Okay. So first of all, in the next slides, I'm going to show that this object here actually exists and behaves sensibly under some conditions. So remember, we needed to show that the mean embedding existed and didn't just have, you know, infinite expectation and blow up. Okay. And to show that, I'm going to show that this C, so this covariance object, is itself in a Hilbert space. Like, it's a more complicated Hilbert space, but it's in a Hilbert space just in the same way that the mean embedding was in a Hilbert space. Okay. So the first thing I'm going to gain from understanding how this C operator works is a quick way to compute the constraint covariance empirically. Okay, so I've been looking for like some smooth functions that maximize the covariance. Once I have an idea of what this covariance operator in feature space looks like, it will become very easy to compute the constraint covariance on the basis of samples. The next, and I think more interesting thing that arises is at the moment that I understand what this C is, I can think of different ways to sort of look at this object and just trying to find this maximum covariance. Okay, and these will also sort of give me information about my data that this maximum covariance didn't give me. And as an exercise after I've done this, it would be fun to revisit kernel PCA using all of the tools that I've mentioned. So that's just a fun thing that I suggest. Okay. So the first thing to do is actually to set up, unfortunately, a certain amount of mathematics. So I need to show that this object here is in a Hilbert space, okay? And so I'm now going to sort of describe the machinery of the space that this C is in. So it's a Hilbert space, so what I need to show is that, like, what is the dot product on the space where the covariance operator lives, okay? So I'm going to set up a dot product, and then I'm going to show that the covariance operator lives in the space where that dot product exists, okay? Now, the covariance operator is a mapping from basically x, like feature space of, in this case, y to feature space of x. Because like have I got it here? No, I haven't. Okay. I will need to use the board. Okay, that one erases. I think I have enough space. Okay, so what I want to do, first of all, is to define just a space of functions from, well, between two Hilbert spaces, okay? So let's say I have now two different Hilbert spaces, f and g, because like I'm going to have like functions f of x and functions g of y, okay? And both of these Hilbert spaces have a set of basis functions. I'm going to basically define operators on these spaces. So these are sort of analogous to matrices, which are sort of n by m matrices. So you can imagine an operator between two, like, as a simple case, let's say that f, is Rn and g is Rm, okay? So I want an operator L from f to g. What this looks like in linear algebra is L is basically a matrix with m rows and n columns, right? Because if I do L times a matrix in Rn, which is A, okay, then I get out of it a matrix of m dimensions. So this is, you know, m by n, this is n by 1. So out of that I get a matrix B, which is m by 1. Okay, so this is the sort of intuition you should have in mind when I say that there's an operator from one space to another. Okay, think of this as being like a matrix from one dimension of space to another dimension of space. But I'm making this a little bit more general because these might be, say, feature spaces on images, and these may be feature spaces on text, for example. Okay. Now, since I'm defining Hilbert space, I want to be able to sort of say things like what's the norm and what's the inner product. Okay. So the norm of this object, like this matrix, is basically the sum over all of the basis functions for my space. So these might be, like, if I was in Rn, these would be the unit vectors, like, you know, 1, 0, 0, 0, 0, 1, 0, 0, 0, and so on, okay? So sum over all of these basis vectors of this operation here, which in the linear algebra case is just the matrix vector product. So I just do that and I square it. So that's a reasonable sort of norm. I just like take this operator, I act on all my basis functions, and then I square all of these things. Like, that's a good indication of the size in some sense of this matrix here. Okay? And likewise here is in my inner product, okay? So let's say I've got two of these operators, then the inner product, from which I can recover this norm, because that's the inner product of something with itself, is just the action of this operator on each of the basis functions multiplied by the action of this other operator, okay? So you can prove this thing here is a sensible inner product, okay? Now it turns out that the covariance operator is going to be an object in this particular inner product space, okay? So the next thing that I need to introduce before I can introduce covariances is this idea of like the outer product. So remember when I talked about covariance, I said Cx. It's a good pen. Okay. Cxy is equal to the expectation of x, y transpose, right? So I need some sort of notion of this object here in feature space. And in particular, like I need to sort of show that if I take an object that looks like xy transpose, that's in the Hilbert space that I defined on the last slide, okay? Because, you know, once I've got my xy transpose, I can take its expectation and I've got my covariance, okay? So, by analogy with the linear algebra case, I can define this outer product as being something that acts on a function in the same space as A and spits out the inner product of this second element in A. Okay? So again, let's look at what that means in linear algebra. You've got BA transpose. So this is a matrix. Let's say that's acting on an object F, which is a vector. So this is like an n by 1 vector. That's equal to, well, A transpose F, which is the inner product of A and F, multiplied by the vector B, which is m by 1. Okay? So you can see this is taking a vector in space n by 1 and outputting a vector in space m by 1. Okay? So what I want to do is sort of define something like this in infinite dimensional spaces, and I want to make sure that, like, you know, it's got finite norm, its inner product makes sense, all of those sorts of things. Okay? So I can write this down and I can say that this is something that does exactly what the linear algebra one does. And then I want to make sure that it's in the Hilbert space that I've defined. So is this intuition clear? Yeah? Okay, so this is actually a really short proof. What we want to make sure is, does this thing here have finite norm? If it has finite norm, it's in the Hilbert space. Okay. So remember how we've defined the norm. We've defined the norm of the sum over all basis functions. So these are the like coordinate axes in my perhaps infinite space. Of this operator here acting on these, take the norm and square it. Okay? Now, at this point, I can use the fact of my definition of this operator here. Okay? So remember, B cross A acting on this thing here is just the inner product of A and E, inner product of A and E, which is a scalar, multiplied by this B thing here. Okay? So, you know, let's do that. So we've got this next line. Now, notice that this thing here is a scalar, so I can take it outside the norm. Okay? So then I've just got the norm of B times all of these guys. Okay? So I've got like a sum of norms of B times each of these terms. So the norm of B is common to all of them, so I can take it out the front. Right? So now I've just got the norm of B times A inner producted with this basis function squared. Okay? Now we already know what the sum of A inner producted with the basis function squared is. It's just the norm of A, in exactly the same way that this is the norm of B cross A. And so we just have now the norm of A times the norm of B. Okay? So basically, as long as A in its own feature space has finite norm, and as long as B in its own feature space has finite norm, then this B cross A thing in the Hilbert space of tensors, like in this F cross G space, also has finite norm. So this is a quick way to guarantee whether or not this thing here exists. As long as each individual term exists in its own space, then this thing here is in the Hilbert space we're trying to define. So does this reasoning here all make sense? Are there questions about it? So a good way to like think about this is just to do everything in N and Rm using linear algebra, and like all of these steps will just follow through pretty clearly. But you know, they work just as well in the infinite case as in the finite case. Okay.
So what's passable is that interesting?
That's just what's telling
step.
me that this is equal to that. Yeah, exactly. Yeah. Okay, so now I've got my like BA transpose style object. Okay. My next trick is actually to see what happens when I apply this B transpose A style object to some other function in the same space. Okay. And I'm going to do this because it's going to be like something I'm going to need to use. So for the proof of that, I think I'll try and use the board even though I don't have a lot of it left. If I run out of board space, I will just go to the slides. Okay. So what I want to show is this. I want to show that the inner product in this space of L and B cross A is this thing here. Okay. So the best way to do this, I think, is just basically like to write both of them down and to show that they're the same. Okay, so let's start with the, let's check, actually, what is this? Okay, so let's start with this one, L B cross A. Okay, so remember, I'm just going to use the inner product of the definition now. I equals I times L E I and B cross A E I. Okay, this is just the definition of the inner product, so I haven't done anything fancy here. Okay, the next step here, we've got I E I L E I. Now remember, B cross A E I is just B times A E I, right? And that's true because I've defined my tensor product. That's just by definition of my tensor product, right? So this is equal to the sum over I of inner product of A E I and L E I B. Now at this point, I'm going to use something which I'm going to keep up here because I'll need it a few times. I'm going to say that the action of L on EI, so on this basis function here, can be expanded out sum over J of alpha J I F J. Okay? So remember this L operator here, what it's doing is it's taking something from the F space and mapping it to something in the G space. Now I've defined E to be my basis functions in F space. I'm going to write it here, EI are the basis functions in F space, and then these little Fi's or Fj's are going to be the basis functions in the G space, okay? And I'm going to know that L is the mapping from F to G. Okay, so what I'm basically saying in this line here is that the action of L on E can be like this is just a function in the G space, and it can be expanded in terms of the basis functions, which is like not a very I guess controversial thing. Okay, so now I've got these LEs acting on B, right? I A E I. Now I'm going to put my L in here, so that's J in J, alpha J I. So the coefficient for the Jth basis function representing the I in the F space, and then Fj, and then productive with Bj. Okay, so I hope everyone reached this, by the way. I think you're in an unfortunate position. Well, yeah. Okay. Maybe I should use the slides, but that's not as fun. Okay. And so if you've got that, yeah, then all you've got after this is basically sum over I in I, then my J here, J in J, times alpha J I, times AEI, times BFJ. Okay, so I've expanded this operation out, and what I've got out of it is the sum over all my basis functions for A, all my basis functions for F inner product with A, all my basis functions for G inner product with B, and then some coefficients which are basically my representations of this L. So I've got my A, I've got my B, and from my alphas I've got my L here. Okay? So I've shown how to do this thing here. Now I want to show the other side. So now I want to show how I want to do this here. Okay? So let's remove all of this. And now let's start with something else. So basically B, L, A this time. Okay? And so let's now write A is equal to the sum over I of A, E, I. So what have I done here? I've just basically expanded A in terms of the basis functions E. Okay. So these are all orthogonal, so it's sort of like, inner product of A with each of the coordinate vectors times its respective coordinate vectors. That's going to give me back A, okay? So let's start with this. So now we've got is equal to B, inner product of L, and sum over I, A, EI. I've just substituted this back in here. Okay, and so this is equal to, I'm going to try and put it over here and see if it all fits, which is basically B L E I, oh sorry, sum over I of L E I times A E I. Okay. Now I've got my LEI here. Okay, so this is sum over B of sum over I, sum over J, alpha J I, Fj. So this whole thing here is just LEI from up here. Then I've got this times A I. Now you notice that I kept this bottom line here because it's the same answer. Okay? When you do this, you get the sum over the B's and Fj's, B's and Fj's. You've got your alpha Ji's, you've got your AEI's here. So basically, with a bit of algebra, I've shown that these two things are equal. Okay? So all of this is in the slides, but I don't like doing proofs on. So is that clear? Yeah? So now I've shown basically how to take this tensor product and make it act on some other operator in the same space. And I think probably I will continue next time. We're out of time.